Hi, everybody. Welcome to phase diagrams and heat presentation. It is 11:45 at night, and my family is going to come down and yell at me for making so much noise during this presentation. But that is the way it goes. There we go. All right, let's get started. What I would like you to do is to have out a piece of paper and to be able to actually take some notes right now. Some of you might want to use Google Keep, is that what it's called? To take your notes, and that's fabulous also. If I talk too fast at any time, please pause me so that you can get caught up and then work ahead. So what we're going to do, we're starting our gas unit. We're going to talk about gas laws. And before we do that, we want to talk a little bit about what is a gas and a little bit about heat and temperature and what's going on when we switch phases and get into the gas phase. So we're going to start today by talking about the phase change diagrams and how to interpret these phase change diagrams. And what you're going to notice is that they all look a little bit different, but they have some important similarities. And so we're going to take a look at them, see if you can interpret them, and then tomorrow we'll actually start in on the gases and talking about gas laws. All right, so before we talk about anything else, we're going to have a whole unit where we talk about heat, but I'm just going to introduce the concept of heat. What is heat? Heat is a form of energy that flows between two samples of matter because of their differences in temperature. So heat is being transferred from the warmer to the colder, and heat relates to phase changes, and we're going to learn a little bit more about that as we go. So here's another phase diagram. This particular phase diagram has to do with water, and what we're going to learn is that every phase diagram is a little bit different based on the substance itself. So it says here the graph showing the states of the substance under different conditions of temperature and pressure, and the phase diagram is different for each substance, reflecting the different boiling and freezing points. So if you were to just study the one from water right now, you can see there's temperature along the horizontal axis, and there is pressure along the vertical axis. And then notice the light blue is a solid, the purple is where it's liquid, and the what ugly color brown that is where it's a gas. And then take a look at some of the other things. Critical point, triple point, we're going to talk about all of those in just a moment. All right, you don't need to draw this yet. I'm going to have you draw a phase diagram, so you need to have that paper and pencil or your Google Keep ready to go. So it says, first of all, note the position of the solid, liquid, and gas. So it's SLG. That's the way I always remember it. So the green is the solid, blue is the liquid area, and the beige is the gas area. Very generally, if you have low temperatures, look all the way on the temperature axis, go all the way axis. I always say that wrong. Go all the way to the left. And that is my left, right? Yeah. And notice at low temperature, but high pressure, you have a solid. On the opposite end, if you go very high in temperature and have low pressure, that's where the gases are located, and then the liquid would be somewhere in between. Okay, now is when I want you to actually take out a paper and pencil and make sure you're drawing this diagram. I am unfortunately not a huge fan of this particular graph. I like these other graphs a little bit better. This one I like a lot. This one I'm not a huge fan of, and yet it's been labeled for us, so we're going to go with it. But so would you draw what looks kind of like a letter Y? So give me a X and Y axis. So give yourself temperature along the bottom and pressure along the side. And then draw a roughly shaped letter Y using the lines. And then label, listen carefully before you write it, label solid, liquid, and gas. But you're going to add like 10 labels to this graph. So make sure that you give yourself plenty of space for labeling. Okay, so what we're going to label is what's going on in this graph. So you should be able to figure out a lot of it all by yourself. So if you wanted to show, for example, where the melting point is, how would you figure that out? Well, melting is when you go from a solid to a liquid. So that's when you're going to cross the line between the solid and the liquid. So we're going to label all of those places. So melting is happening where the red line is. So I want you to draw a red arrow pointing from solid to liquid, and then I want you to write melting by it. I'll give you a moment to do that. And now freezing, of course, would be going exactly the opposite direction. Freezing is when you're going from liquid to solid, so that would be where the blue arrow is, and then you'll want to label that. You want to have space to label that. Okay, and then vaporization or vaporizing is when a liquid is going from a liquid to a gas. So that would be the orange arrow. Crossing that line is when you're going when the molecules are going from a liquid into a gas. And then of course condensing would be exactly the opposite, when we're going from a gas into a liquid. When the gas is cooling, it becomes a liquid, and that's condensation. So that's the green arrow. I'm trying to talk a little bit to give you time to write it down. Pause me if you need to. I'm just going to move ahead so I don't wake up my family. All right, now the two that you might not be familiar with, I'm not sure if junior high teachers talk about it, but sublimation and deposition. So sublimation is changing from a solid to a gas without first becoming a liquid. What? That's weird, going from a solid to a gas. So like water, when it's ice, it melts and goes into water, and then it boils and it becomes a vapor. How is it that could ever go from a solid to a gas? Well, it does. And almost everybody's noticed that in your own freezer. If you look at your ice cubes, old ice cubes are small, like they shrivel up over time. If you haven't noticed it, pay attention. That's called sublimation. And that's when the water molecules, the frozen ice water molecules, get up enough energy to escape without becoming a liquid first. They just leave and enter your freezer. And so it has sublimated, and that makes the ice get smaller. Your ice cubes get smaller. Deposition, you have also all observed. I'm going to move my thing there. Deposition is changing from a gas to a solid without becoming a liquid first. So this you've seen when you see frost on a window. You have water vapor in the air. It touches a cold window, and instead of passing through the liquid phase, it goes from gas immediately to a solid, where it's the frozen ice on the window itself. So that's what frost is. So that's deposition, and that would be the pink arrow that you have here. So going from gas to solid. So sublimation and deposition are probably two new words for a lot of you, and they are opposite words. Okay, I'm just waiting to give you a chance to write. Okay, we're moving on. We have a couple more things I want you to label on this diagram. First of all, we want to label the triple point. The triple point is defined as, and you might want to write that down below, just like you might have wanted to write down sublimation and deposition, the definitions, just so you're familiar with them. You might want to write down triple point. Triple point is a set of conditions where all three phases can exist at the same time or in equilibrium with each other. So if you look at this diagram, my guess is you can figure out where the triple point is. Guess going, and the triple point is where the red dot is. So get that red dot and write triple point. That's where all three phases are occurring at the same time. All right, and then we're going to end, and this is part of why I don't like this diagram. This diagram was not drawn well. This line should continue up, and this line should continue down. So the diagram isn't drawn very well, but we're going to go with that. So listen, the critical point on one of these phase diagrams is the set of conditions where beyond this point, the substance is forever in the vapor phase. So beyond this, at a higher temperature and higher pressure, it's always in the vapor phase. And that critical point is, right at the end of this line right here. So this is called the critical point, and you want to label that on your diagram. And I'm giving you a chance to label it, so I'm wasting a little time. Pause me when you need to, and I'm going to move on. Okay, so this is just one more example. This is a much better drawn graph. So temperature is increasing along the bottom, pressure is increasing along the side, and then you can see it just asks where's the melting point and the boiling point. Well, melting point is labeled very clearly for us, but what's the boiling point? Well, let's think that through, because that's not actually labeled. Boiling is where you're going from liquid to vapor, so that's vaporization. So the boiling point we're going to look for in just a second. This is showing you melting, but which point exactly is where it's melting? Like, where on this line is it melting, and where on this line is it boiling? And we'll get to that in just a second. So before we can actually answer that question, we're going to talk about a couple things. Oh my gosh, does this strike horror in some of your hearts? This is the mole roadmap. Some of you might remember that we used this in our mole unit during term one when we wanted to convert from grams to moles. You just did a million of those in stoichiometry. But then in our mole unit, we also went from moles to atoms or molecules. So do you remember Avogadro's number 6.02 times 10 to the 23rd? And some of you are like, no, never heard of it. You did hear of it a long time ago. Anyway, so if you wanted to convert something, let's say you had 62 grams of hydrogen gas and you wanted to know how many atom or how many molecules of hydrogen gas you had, you would go from mass, from grams to moles and convert it into moles, and then you would go from moles to particles or molecules in that case. And now what we have not seen before is this, or what we haven't used before is this branch of the mole roadmap. And that's what we're going to get to in the gas laws here. So 1 mole, remember, equals 6.02 times 10 to the 23rd particles, Avogadro's number. Now the molar volume of a gas means, what does that mean? It means the amount or the volume that 1 mole occupies at 0 degrees Celsius and 1 atmosphere of pressure, which is called standard temperature and pressure. So 0 degrees Celsius and 1 atmosphere are known as standard temperature and pressure. So once in a while, you'll see in our papers or our labs STP. Unfortunately, STP varies by industry. So technically, we shouldn't say STP. We should say 0 degrees Celsius and 1 atmosphere of pressure. However, we get lazy and we write STP. And it's just, you have to make sure within your class, within your industry, that you're talking about the same STP because it does vary. For us, it's going to be 0 degrees Celsius and 1 atmosphere of pressure. All right, so 1 mole of gas occupies, Avogadro figured this out, 1 mole of gas occupies 22.4 liters at STP, at 0 degrees Celsius and 1 atmosphere of pressure. So because it doesn't matter what the gas is, it always occupies 22.4 liters at STP, which is a crazy thing when you think about it. We'll learn more about it in a little bit. You can use that 22.4 as a conversion factor, 22.4 in 1 mole. So for every 22.4 liters, there is 1 mole of that gas. And so you get to use that on this part of our mole roadmap. And now we know how to use all parts of the mole roadmap. So let me go back to my original idea where I said, what if you had 62 grams of hydrogen gas? How much volume would that take up? So you would convert those grams into moles, and then you would convert the moles into liters by using these conversion factors. So now, the original question back on the last slide was, what are the melting point and what are the boiling point? So now let's take a look. Oops, I forgot. We have to just mention this really quickly. There are different units, just like we use Fahrenheit in the United States, which is the stupidest measurement ever. Sorry. Bias. Okay. So in chemistry, we use Celsius or we use Kelvin. Kelvin is interesting. You don't use degrees with Kelvin. So 273 Kelvin is the same as 0 degrees Celsius. So those are interchangeable terms and you absolutely need to know them. So you got to write them down. Well, you'll see them and you'll need to be able to convert between the two. 0 Kelvin is absolute zero, and we'll talk about what absolute zero is coming up a little bit later. And then pressure, the ones that you're going to see the most are 1 atmosphere of pressure and 101.3 kilopascals. You might see 760 millimeters of mercury. That's what mmHg is. But I don't think in this class we're ever going to use 760 torr. It's possible that we would see that. So I want you to write all of them down so that you can be able to change or be able to go back and forth between those different units. All right, and now the last thing that we're going to talk about is coming back to the phase diagram. Our question a few slides ago was, what are the melting point and what are the boiling point? Well, melting point and boiling point vary depending on the pressure and the temperature. So if our This is where melting occurs, where we go from a solid to a liquid. At this temperature and this pressure, it's different than at this temperature and this pressure. The melting and the boiling point vary. So what we want to do is know what is the melting point and boiling point at STP, at standard temperature and pressure. So it says so draw a horizontal line across the diagram. You could draw it in your own diagram that you have. You could make a 1, that could be your atmospheres, and draw a straight line across and have it hit both lines. So where the line hits the solid liquid boundary, that's this one right here, that's the melting point. You could write MP if you wanted to. And then where the line hits the liquid vapor boundary, this line here, then we're going to call that the boiling point. And that would change, the melting point and boiling point change again if the temperature or the pressure change. But if we are at STP, if we're at standard temperature and pressure, then those two things are consistent. Okay, are there any questions? Oh, you can ask me questions, I forgot. So that's it, you guys. We're going to wrap that up today. Let me know if you have questions. Have a good night. Bye.